Welcome to my channel RT Physics. This is a lecture series on atomic and molecular physics, and this is lecture 11 of the series. Today we are going to study electronic configuration and Hund's rule. For the chemical properties study as well as for understanding the physical properties of the atoms, it is necessary that we understand what is the arrangement of electrons inside the atoms, or what is the atomic structure. So the shell model of atom, or the shell model of electron configuration inside the atoms, suggests an arrangement of electrons in different shells and subshells. Two basic principles determine the structures of atoms with more than one electron. First one is, a system of particles is stable when its total energy is a minimum. This is the principle which is followed by all the stable systems. And the second principle is, only one electron can exist in any particular quantum state in the atom. This is Pauli's exclusion principle. So these two principles, which are related to the energy of the physical system, that is atom, these two principles decide or determine the electronic configuration. So the first principle talks about the minimum energy arrangement of electrons, and the second principle talks about the quantum state that is decided by the quantum numbers, and the Pauli's exclusion principle, which states that electrons have to differ at least in one quantum number from each other. So these two principles decide or determine the electronic configuration inside an atom. Electrons that have same principal quantum number n, usually, though not always, are at the same distance from the nucleus. These electrons therefore interact with roughly the same electric field and have similar energies. Such electrons occupy the same atomic shell. So the principal quantum number n, which determines Bohr radius according to Bohr atom model. So if the principal quantum number is same, we say that the electrons are in the same shell or in the same orbit. So therefore, as in Bohr atom model, the radius of the orbit is decided by this principal quantum number n. So therefore, we can say that the electrons which are in nth shell will be at the same distance from the nucleus. And these electrons will therefore experience almost similar force, that is almost similar interaction with the nucleus as well as with the other electrons. So therefore we can say that they have similar experience of the electric field, and so they will have similar energies. Such electrons are said to be in the same atomic shell of principal quantum number n. So we can say that the principal quantum number n decides the shell of the electron in an atom. So if n takes values 1, 2, 3, 4, 5, etc., then the name of the shell is K, L, M, N, O, etc. That means principal quantum number n is equal to 1, that means it is K shell. If the principal quantum number is 2, it is called as L shell, and so on. The energy of an electron in a particular shell also depends to a certain extent on its orbital quantum number L. though not as much as on n. We know that corresponding to each principal quantum number n, there will be orbital quantum number L which can take values from 0 up to n minus 1. So for example, for n equal to 1, that is for K shell, there is only one orbital quantum number, that is L equal to 0. Okay. For n equal to 2, L can take values 0 and 1. These uh, these uh, these orbital quantum numbers L, each one of them is given or is associated with a letter. For example, L equal to 0 is called as S subshell. L equal to 1 is called as P subshell. So electrons which share a certain value of L in a shell are said to occupy the same subshell. For example, if electrons are in L equal to 1, then they are said to be in P subshell. Okay. Or if they are in L is equal to 2, that means they are in D subshell, and so on. All the electrons in a subshell have almost identical energies. Since the dependence of electrons energy upon ml and ms is comparatively less, we know that each L subshell or each L quantum number has 2L plus 1 ml values. Okay, and because each electron has spin quantum number s, which is equal to half, and so there are two values of ms, plus half and minus half. But these ml and ms, they do not give rise to much energy changes. So therefore there is more dependence on or we take into consideration L quantum number if we are considering the energy of the electrons. Now the occupancy of various subshells in an atom is usually expressed as follows. Each subshell is identified by its principal quantum number n, followed by the letter corresponding to its orbital quantum number L. A superscript after the letter indicates the number of electrons in that subshell. So for example, electron configuration of sodium, which has atomic number 11, is written as 1s2, 2s2, 2p6, 3s1. See, here 1 signifies that the principal quantum number is 1. S signifies that orbital quantum number L is 0 and there are 2 electrons in this S subshell. Similarly, there are 2 electrons in 2s subshell. That is, in shell number 2, this is the S subshell. In shell number 2, there is P subshell also, and it has 6 electrons. And in the third shell, again there is S subshell which has 1 electron. Now, how we can decide how many number of electrons are there in each subshell? So, for that, we have to consider the Pauli's exclusion principle. So, the shell and subshell capacities, how they are decided. Capacities means what are the maximum number of electrons that a shell or subshell can accommodate. So, the exclusion principle limits the number of electrons that can occupy a given subshell. A subshell is characterized by a certain principal quantum number n and orbital quantum number L, where L can take values from 0, 1, 2 up to n minus 1. So maximum there are n values possible for the quantum number, orbital quantum number L. there are 2l plus 1 different values of magnetic quantum number ml for any L. Since ml can take values 0, plus 1, minus 1, plus minus 2 up to plus minus L. And finally, the spin magnetic quantum number ms has two possible values, plus and minus half. Okay, so now there are four quantum numbers that we are going to consider. That is, first is principal quantum number n, then orbital quantum number L, which can take values up to n minus 1. Then ml, magnetic quantum number, orbital magnetic quantum number, which can take from 0 up to plus minus L, that is 2L plus 1 values for any given value of L. And each electron will have a spin quantum number ms, which can take values plus half or minus half. Therefore, the number of electrons that a subshell can contain is maximum 2 multiplied by 2l plus 1 electrons. This 2l plus 1 because of 2l plus 1 values of ml, and this 2 because there are two values of ms. So each subshell means for each quantum number L, one can have maximum 2 into 2l plus 1 electrons. So therefore, S subshell, which has L equal to 0, will have 2 into 0. So that will be 0 plus 1. So 2 into 1, that is maximum 2 electrons. For P subshell, L will be 1. So 2 into 1 plus 1, that is 3 multiplied by 2, maximum 6 electrons in the P subshell, and so on. The maximum number of electrons a shell can hold is sum of electrons in its filled subshells. This number is 2n square. Okay, so each subshell can have 2 into 2l plus 1 electrons, and each shell can have maximum of 2n square. So that means the first n is equal to 1. N is equal to 1 can have maximum 2 into 1 square. 2 into 1 square. 1 square is 1. So maximum 2 electrons are there in the first shell or K shell. If n is equal to 2, then 2 square is 4. So 4 multiplied by 2 means the second shell can have maximum 8 electrons, and so on. The order in which electron subshells are filled, this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and so on. This sequence is according to the increasing energy of the different shells and subshells. So here you can observe that after 3s2, 3p6, 4s2 is placed before 3d10. Though D is a subshell of third shell, that is principal quantum number 3, in spite of that, we can see that because 4s subshell, it is of lower energy as compared to this 3D. So therefore, this is filled first before this 3D. Okay. Similarly, after 3D, this is 4p6 and then 5s2 before 4D. So 5s2 will be filled before 4D, and this sequence is according to the increasing energy of different shells and subshells. Now one more important rule. regarding the electron configuration is Hund's rule. This rule tells us about the arrangement of electrons in a particular subshell. In general, the electrons in a subshell remain unpaired. That is, the electrons will have parallel spins whenever possible. This principle is called as Hund's rule. So, the electrons in a subshell are arranged such that they will remain unpaired as far as possible. The explanation of ferromagnetism of iron, that is the magnetic properties of iron, cobalt and nickel, can be explained by using Hund's rule. This is a consequence of Hund's rule, that is the ferromagnetism of iron, cobalt and nickel. This is a consequence of Hund's rule. If we look at the atomic numbers of, for example, of iron, then the 3D subshells of these atoms are only partially occupied, and the electrons in these subshells do not pair off. So their spin magnetic moments do not cancel out. In iron, for instance, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So we can observe that there are 6 electrons in the outermost, that is 3D subshell. If we look at the 5 orbitals of this 3D subshell, then what we can see, these 6 electrons are arranged such that initially the 5 orbitals are occupied, and then the 6th electron is paired with the first orbital electron. So there is only one pair, and these 4 electrons are unpaired. So the spin magnetic moments of these electrons are not cancelling each other. Okay, when the spin magnetic moments can cancel out if electrons are paired, like in this case. Okay, so though there are even number of electrons, means 6 electrons are there, so there can be 3 pairs of electrons, but we can see that there is only one paired electron, okay, one pair of electrons with opposite spins, and the remaining 4 are unpaired. And this is because of the Hund's rule. And so because of this unpaired electrons, there will be a large resultant magnetic moment, and this is happening also in case of cobalt and nickel, which are having just one electron more as compared to, means cobalt is having 1 electron more as compared to iron, and nickel is having 1 more electron as compared to cobalt. So the next electron of cobalt will be paired up with this electron. Okay, so again there will be these 3 unpaired electrons. For nickel, this will be paired, so 2 electrons will be unpaired. Okay, so the magnetic moment will go on decreasing in case of cobalt and nickel as compared to iron. Okay, so we were considering the case of iron, and 5 of the 6 3D electrons have parallel spins, so that each iron atom has a large resultant magnetic moment, and therefore this is showing this ferromagnetic properties. So the ferromagnetism in iron, cobalt and nickel can be explained by using Hund's rule, that the electrons will try to remain unpaired as far as possible. Now one more example we can see over here, or one more application of Hund's rule, we can see if we consider the electronic configuration of these various elements: boron, carbon, nitrogen, oxygen, fluorine, neon. Atomic number of these elements varies from 5 to 10, and we can see that the uh, first 4 electrons are filled in 1s and 2s subshell, and the p subshell is filled in this fashion such that initially only single electron will be filled in each orbital. Okay, so boron has only single electron in the 2p subshell. Then the next, that is carbon with atomic number 6, will have 2 unpaired electrons. Remember that this p subshell has 3 orbitals that corresponding to 3 values of ml, that is -1, 0 and +1. Okay, so there are 3 orbitals available. So in case of nitrogen, these are the 3 electrons which will remain unpaired, and in case of oxygen, first pair of electrons will be formed. In case of neon, all the 3 electrons are paired. Okay, we can see that there are 3 pairs of electrons, and so therefore because all the electrons are paired, now neon is an inert gas. Okay, the origin of Hund's rule, or what is the physical significance, or what is the physical reason behind Hund's rule, that we can see if we consider the mutual repulsion between the electrons and its relation to the energy of the atom. Now, because the electrons are negatively charged particles, so electrons among themselves, they will repel each other. Electrons in the same subshell with same spin must have different ml values, and so they are described by wave functions whose spatial distributions are different. Remember that each subshell has 2l plus 1 ml values, and each of these ml value correspond to one orbital. Okay, so these different orbitals are described by different wave functions. The electrons will be away from each other in space if they are placed in these different orbitals. So electron with parallel spins are therefore more separated in space than they would be if they are paired off. So if the electrons are in different orbitals corresponding to different ml, then they will be separated in space and are having parallel spins. Then they are occupying different orbitals, so they will be separated from each other. This arrangement is of less energy, as we have seen. So this completes the discussion on Hund's rule. Thank you.